In this video, we're going to talk about rational functions. Here I have Desmos pulled up, and I have the graph of the parent function of a rational function, 1 over x. Most rational functions look like this. There's two parts to it, and they're going to have some vertical asymptotes, right? It never actually touches 0, this x-axis, or I'm sorry, the y-axis, and same thing for the x-axis, right? I have a horizontal asymptote, my end behavior asymptotes that we were talking about yesterday. So most rational functions are going to look like this, but we also do have some examples where rational functions have 3 parts, kind of crazy. It looks like this, or even this very last one, rational function kind of looks like slanty, but again, has 2 parts there. So what we're going to do today is we are going to be able to talk about the different key features of our rational functions. So we're going to look at this very first one here, this x plus 1 over x squared plus 2x minus 8. And we're going to be able to pick out all of the key features without even looking at the graph. So go ahead and write down number 1, this function, and we're going to be able to identify all these different key features. So step number 1 is to find the vertical asymptotes, which is going to result for when we factor this polynomial here in the denominator. So I have x plus 1 in the numerator, and I know the denominator would factor into x plus 4 times x minus 2. So our vertical asymptotes are basically go with the domain. It's all of the values that x cannot equal. It's a fraction, so just like we would do domain way back in Unit 1, I know that in a fraction, my denominator cannot equal 0. So my vertical asymptotes are going to be the same thing as the zeros of this denominator. So my 2 vertical asymptotes are going to be x to be negative 4 and x equals 2. Okay, so that means on my graph, I'm going to draw those as dotted lines because they're not actually part of the graph, but I know when I graph my function, my graph is going to get really, really close to those values, but it's not going to cross those. So that's going to go with my domain, right? My x values, it's going to be from negative infinity to negative 4, from negative 4 to 2, and then from 2 to infinity. Okay. The end behavior asymptote is what we talked about yesterday. That is has to do with the degree of the numerator and the degree of the denominator. In this case, the degree of the numerator is 1, the degree of the denominator is 2. So anytime the degree of the numerator is less than the degree of the denominator, your end behavior asymptote will always be y equals 0. So here we have kind of like a horizontal asymptote there at y equals 0. The x-intercept and y-intercept can always be found in the same way. The x-intercept is always some number comma 0. So we're trying to figure out what number could we plug into the equation that would make the whole thing equal 0. And kind of like a shortcut to that, it's always going to be the zeros of the numerator. So my x plus 1 is my factor in that numerator. My x-intercept is going to be at negative 1. If I plug negative 1 in, we're going to get 0 for the whole fraction. So my x-intercept I know is negative 1, 0. My y-intercept is the reverse, right? Is 0 comma something. So that means all my x values are going to be 0. So you're going to plug in 0 for all of your x values. I honestly think it's the easiest when you look at the original function and you just plug 0 in for all of those x values. All you're going to be left with is 1 over negative 8. So that's going to be our y-intercept. 1 over negative 8 or negative 1/8. Okay. There is not a hole in this function. We'll talk about what a hole is in the next example. And then we can kind of cheat because we did see on Desmos what this looks like. Again, we'll kind of talk tomorrow more about specifically how to get these graphs without looking at Desmos. But we're cheating for today, and we know this graph is going to look something like this. Right? Again, we get really close to those asymptotes, but we don't actually cross them. And so we can see on here that even though our end behavior asymptote is y equals 0, I do have an x-intercept, so my range is going to be all real numbers, negative infinity to infinity. There's not a y value that we jump over. Let's look at this second equation. go ahead and pause the video and try and find those vertical asymptotes and the x-intercept, or just do the vertical asymptotes and end behavior asymptote. This one is actually a really special case because when we go ahead and we factor both the numerator and the denominator, we could see that we get the same factor in the numerator as we do in the denominator. So anytime we're multiplying things and I have the same thing in the numerator and the denominator, we know that those cancel out. So this function is actually much more simplified than what we started with. And this is the rational function that we're looking at. So two things that we just discovered. So we're still looking for those vertical asymptotes to be the zeros of that denominator. So here, our vertical asymptote is still going to be x equals 3. Our end behavior asymptote still has to do with the degree of the numerator and the denominator. Here, because they're equal, remember we look at the ratio of the leading coefficients. So the leading coefficient of the numerator is 2, and the leading coefficient of the denominator is 1. So we get 2 over 1, or y equals 2. Okay, so our end behavior asymptote is going to be up here at 2. Our vertical asymptote is going to be at 3. Okay, what we do with the 0 that we canceled out, since we had that x plus 2 and x plus 2 in the numerator and the denominator, that actually becomes a whole. Okay, a whole with my x value at that 0. So it was x plus 2, so I know my whole is going to have an x value of negative 2. So that means that on the graph, I'm literally just going to jump over. I'm going to have an open circle at that point, okay, a whole. And in order to figure out what the y value of that whole is, I'm going to plug in that x value into my new equation. So I'm going to plug in negative 2 into this equation, and my output is going to be what I get for my y value for my whole. So we get negative 6 over negative 5, or positive 6 over 5. Because both of them are negative, it changes into positive. So that means at this point, negative 2 and then 1 and a little bit more. I'm literally going to have a whole. I'm going to have an open circle on my graph. So that's the only difference between number 1 and number 2, is that in number 2, I had a factor that canceled out in the numerator and the denominator. So now that's considered my whole. Okay. Everything else is going to go through in the same way. So I'm going to go ahead and I'm going to fill in the x and y intercepts. So remember my x-intercept, I look at the numerator and I take the zeros. So I do look at the new function after we canceled out those factors. So we get 1 comma 0. And remember the y-intercept is when we plug in 0 for all of the x values. So we get negative 4 over negative 6, which simplifies to that positive 2/3. So negative 1, 0, and 0. 1, 0, and 0, comma 2/3. Okay, so we can start to see that this is what our graph is going to look like over here. Again, we didn't even look at Desmos there. And then I know my rational function is always going to be symmetric on the other side, like that. So going through and answering my domain, making sure you account for the whole and the vertical asymptote. So from negative infinity all the way to the x value of my whole, which is 2, union negative 2 all the way to my vertical asymptote, which is 3, and then 3 to infinity. And then the range, same thing. Make sure you're accounting for any horizontal asymptotes, that end behavior asymptote, and the whole as well. So from negative infinity all the way up to the y value of my whole, which is 6/5. And then we're going from 6/5 all the way to my end behavior asymptote of 2, and then from 2 to infinity. So a little bit more complicated. All right, number 3, same thing. Let's go ahead and find the vertical asymptote and behavior asymptote and see if there are any holes in this graph. Okay, so after we factor, we see that there are no common factors. Nothing's going to cancel out in the numerator and the denominator, so I know that there are no holes. The zeros of the denominator are negative 2, and because the degree of the numerator is greater than the degree of the denominator. Remember, this is what we talked about yesterday. We have a slant asymptote. So in order to find that slant asymptote, we are going to do some synthetic division with the numerator and denominator to figure out that slant asymptote. So we're plugging in, or we take -2 and we're going to synthetically divide it by the coefficients of the numerator. And we get, remember, we do not care about the remainder anymore. This is our constant, this is our x term. So our answer is our slant asymptote x plus 2. So that's a linear function with a y-intercept of 2 and a slope of 1. So our slant asymptote is going to be the graph of that equation. Go ahead and find the x-intercepts, y-intercepts, domain and range. We're going to, again, cheat. We'll figure out how to do this better tomorrow. But we're going to look at the graph of Desmos to make sure that we have the accurate graph. So again, this is that slanty example. So we have the graph that's going to look something like this, right? It's going to come around our slant asymptote and in both directions here. Okay. So knowing this is going to help us get our domain and range a little bit easier. So the domain is everything except for that vertical asymptote, -infinity to -2, -2 to infinity. And our range, there are no y values that we have to exclude in this graph, so we get -infinity to infinity.